Hey everyone. Last time we had this theorem. This is where we left off, right? It went like this. So if what was it? R is a ring with 1, then the mapping from Z to R given by phi of 1 equals, I guess it's n, phi of n equals n dot 1 is a homomorphism. So just one thing to point out here, right? This 1 right here is the identity, or sorry, the multiplicative identity in R, right? So it's not necessarily the number 1. Right. Anyways, so we know that this is a homomorphism, and this was theorem 27.7. I'm going to refer back to this in our next result. So what we have is a corollary, and I think right before I proved this theorem, I said something to the fact of what we're going to do is show that if you have a ring with 1 / field, right, then it contains a familiar either ring, subring, I should say, or subfield, right? And so that's going to be contained in the next couple of results that we do. So this is corollary 27.8. So let's let R be a ring with 1. And there's 2 parts to this, and it's going to depend on the characteristic of R. So if the characteristic of R is some positive integer n, then R has a subring. So then R has a subring isomorphic to Zn. So there's part A of the theorem. And then part B, so if the characteristic of R is equal to 0, then R has a subring isomorphic to Z. Right, so here's the subring part, right? If we have a ring with 1, then this ring, depending on its characteristic, will either have a subring isomorphic to Zn or isomorphic to Z. Oh, I just don't have enough room here, so I don't like that's a little too skinny. So let's, I'm going to do it over here, and I'm going to kind of erase into my theorem. Sorry that I got to do that, but for the proof, right, so first, part A. So remember, we've got our homomorphism, so let's consider phi from Z to R from 27.7, right? So that takes n to n dot 1. So now, for k in Z, we have that phi of k equals 0. And let me write down the formula there. So phi of k equals k dot 1. That's the formula. And that's going to equal 0 if and only if so remember now, we're working, this was part A, sorry, this is the characteristic n setting. And so when is k dot 1 going to equal 0? Well, it's going to be if and only if k is a multiple of n, right? So if and only if n divides k. Now, and when, and so, okay, so this occurs, right? N divides K, so this occurs if and only if. Well, so what does it mean for K to be a multiple of N? How would we say that ring theoretically? That would be if and only if K is an element of the ideal generated by N. Right? So this occurs if and only if K is an element of the ideal generated by N. So what does that tell us then? It tells us that the kernel of phi is precisely equal to the ideal generated by N. And so we can say this. So the kernel of phi is equal to the ideal generated by N. And now we're just going to apply the first isomorphism theorem. So now phi of first isomorphism theorem Z mod, and let's actually write this out nicely. So what we have is, we know that Zn, we already know that that's isomorphic to Z mod the ideal generated by N, which is equal to Z mod the kernel of phi, which we know is isomorphic to the image of phi, and we know that that is a subring of R, right? So that tells us that Zn is isomorphic to a subring of R. For part B, so let's see, since the characteristic of R equals 0, we have, so now we want to kind of do the same idea. I want to apply the first isomorphism theorem. But what do we have here? We have phi of K, that is, remember, K dot 1, and that's equal to 0 if and only if K is equal to 0. Right? Remember, the characteristic, that's the least N, so that K dot 1 equals 0, well, there is no positive value for which this is going to occur, right? The only time it happens is when K equals 0. And so that tells us, right, that the kernel of phi is trivial. We can say thus, kernel of phi is equal to, right, just 0, right? This tells us it's 1 to 1. So therefore, Z is isomorphic to the image of phi, and that is a subring of R. All right, so anytime if you've got a ring with 1, it is either going to contain a copy of Zn or of Z, depending on what the characteristic of your ring is. Okay, now as a corollary to our previous result there, so this is going to be corollary 27.9, and this result actually, so this is due to Steinitz originally in 1910, and it goes like this. So let's let capital F be a field. 2 parts again. So first part, if the characteristic of F equals P, where P is prime, remember, you proved this in homework, right? Integral domains always have characteristic, if it's not 0, non-zero characteristic, then it has to be prime. Fields are integral domains, so the characteristic of a field is always either 0 or it's a prime number P. So if the characteristic is P, then F has a subfield isomorphic to ZP. And then part B, if characteristic of F is equal to 0, then F has a subfield isomorphic to Q. Oh, so that's kind of fun. So in the proof, notice for part A, there's nothing to do. This follows directly from our previous corollary. So this, so part A, right, follows directly from 27.8. 27.8a. There's not really work to do in part B, but here's the idea. So by 27.8b, F has a subring isomorphic to Z. And now, from this, we want to create something isomorphic to Q. Well, Z is an integral domain. Every integral domain has a corresponding field of quotients. So then, this is from chapter 21, I think. So letting T inside F be, you got to be a little bit careful here. So if you want to actually do the construction, in fact, let me just say who the construction, well, all right, we need to construct fractions, right? So it'd be equivalence classes of, how do I want to say this? No, I'm just going to say it. Okay, so letting T subset of F be the field of quotients. It's really, so letting it be a field of quotients, we have the result. I may be being a little bit hand-wavy here. Here's the idea. We just kind of, you don't need to write this down. But so what we have a subring isomorphic to Z. So let's call that S, right? So what do the elements look like? Well, they're just elements sitting inside capital F. And so then what you could do is, okay, so I guess maybe call it T bar or something like that. That would be equal to, so we could create all the fractions, say A, B inverse, where A is in S and B is in S star. Right, so now we've created all possible fractions. Of course, you have to say what it means for elements to two fractions here to be equal to each other. So you could define the equivalence class in do exactly the construction that we did for the field of quotients, right? Using this notation right here, right? And that will give us who T is, right? So T would be the equivalence classes of these things. I'm thinking of these as fractions here. Right? Take those equivalence classes, that's going to give you T. That will be the subfield sitting inside F that is isomorphic to Q. So if you want, you can work out the details, right? But I'll just leave it at that. Now, one thing that's true, you've seen this before. Intersection of subgroups is a subgroup. Intersection of normal subgroups is a normal subgroup. Intersection of subrings is a subring. Intersection of subfields is a subfield. So let's say it like this. The intersection of all subfields of a field capital F is a subfield of capital F, and it has a name. You can think of, right, when you intersect all of them, you can view this as the smallest subfield of F, right? The intersection of all subfields is the smallest, and this has a name. It's called the prime subfield. Right? So called the prime subfield of capital F. Now, so, and it turns out, so when characteristic of F is equal to P, the prime subfield is isomorphic to ZP, and if the characteristic is 0, so if characteristic of F equals 0, then the prime subfield is isomorphic to Q. Right, so the subfields that we got from the previous corollary, right, turn out to be what's called the prime subfield. They're equal to the intersection of all subfields. This next definition is pretty important. So let's let R be commutative with unity. I think I've already defined this term. Well, kind of. Maybe not quite. So let me. I've almost defined it. So an ideal capital I is principal if there exists a single element, say little r in capital R, such that capital I is equal to the principal ideal generated by little r. So I think I used that term principal in the case when I was first defining the ideal generated by some set of elements. And so now we say an arbitrary ideal is principal if if there exists an R, so that I is equal to the principal ideal generated by some element R, right? So if an ideal has a single generator, then it's a principal ideal. So let's look at a few examples. So first example, let's let I want it to be a non-trivial ideal of Z. So let's let I in Z be a non-trivial ideal, meaning I don't want it to be the 0 ideal. Okay, so it's sitting inside Z. What I'd like to do, so I want to show that every ideal inside Z is principal. Yeah, so let's let little n in I be the least positive element of capital I. And it's going to turn out that this is the generator. So, so then, of course, we have, right, since little n lives inside I, the ideal generated by n has to be inside I as well, right? So we've got containment in one direction for free, just by definition. So now I want to show the opposite containment. So let's pick little a in capital I. I need to show, right, that it lives inside the ideal generated by n. And I think the obvious thing here to do is to apply the division algorithm, right? So, so then there exists a Q and an R in Z such that A is equal to Qn plus R, where 0 less than or equal to R less than N. Okay, so now we know that A lives inside the in I. Qn also lives in capital I. All right, so we can say it like this. So since A and Qn are elements of I, we see that now if I subtract, so R, which is A minus Qn, is an element of capital I. Of course, we chose N to be the least positive element of I. R is either positive or 0, and so by minimality, right, since we said that R is less than N, that forces R to be equal to 0. So by minimality of N, we see that R equals 0, and so let's see, that would tell us that A is equal to Qn, which by definition is an element of the ideal generated by N. Thus, the ideal generated by N is equal to I, which tells us that if we chose a non-trivial ideal, we're guaranteed that it's principal. Also, so we can, just to finish this off, so also, right, the trivial ideal is equal to the ideal generated by 0. And so we can conclude, so final conclusion here. So conclusion is that every ideal in Z is principal. You might want to compare this with the result from group theory that every subgroup of Z is cyclic, right? Principal ideals are sort of the ring theoretic analog of cyclic subgroups. Okay, let's try another example. So in Z bracket X, let I be the ideal generated by 2 and X. We've seen this ideal before, right? So what do elements here look like? They look like 2 times a polynomial plus X times a polynomial. And you can think of this then, this is the set of all polynomials that have even constant coefficient, right? Really, that's what it is. Now, what I'd like to do is I'm going to show that I is not principal, right? Here we have it. Well, okay, fine. It's generated by these 2 elements, and what I want to show is it's impossible to generate this ideal by a single element. So to do so, we say suppose that I is equal to the ideal generated by f of x for some, right, polynomial f of x in Z bracket X. All right, well, that would mean then that f of x equals 2 times g of x plus x times h of x for some polynomials g of x and h of x. Now, in particular, then, that tells us then that f of x has to have an even constant coefficient. So, let's say it follows that f of x has even constant coefficient. Now, since, okay, so now what are we saying here? We're supposing that this ideal here is principal. So that means that there's a single generator that generates, that gives us every single polynomial inside here. In particular, it's going to give us that polynomial 2. Right? So, since 2 is equal to f of x times, let's say, r of x, for some r of x in z bracket x, what does that tell us? It tells us that, so we conclude that, that what, right? So, I mean, we're in an integral domain here. Degrees cannot go up, right, when we do this multiplication. So if I've got degree 0 over here, I've got to have degree 0 times degree 0. And so we conclude that f of x has to equal, well, plus or minus the constant polynomial 2. Right, so now, right, hopefully that makes sense here, right? F has to have even constant coefficient. Then we realize that f has to be a constant polynomial, and so it's got to have even constant polynomial, or so it's got to be an even constant polynomial. So that's our only choices. So now we have also x lives in there. So x has to equal yeah, well, okay, so x, because it's in there, that equals f of x times some polynomial sx. That's going to equal plus or minus 2 times polynomial sx. That just can't happen, right? Whatever this polynomial is over here, you're not going to be able to find a polynomial, yeah, I should say it this way, no matter what s of x is, you are not going to have this equal to x on the other side, right? All right, so let's just say, which is possible. Therefore, all right, so we have a contradiction here. I mean, I guess I was a little weird when I answered this. So what do we have? We have an odd coefficient right here. There's a 1 right here, right? And over here, all the coefficients are even, right? So we've got an odd coefficient equal to a polynomial that has all even coefficients. That's impossible. So therefore, 2 comma x is not principal. I think I'm gonna leave off. Well, okay. So this leads us to a definition. These two examples here. So an integral domain in which every ideal is principal is called a principal ideal domain. And now, looking at the two examples we just did, what we have is, so Z is a, you always abbreviate principal ideal domain, PID. A lot of people actually say PID. I don't say PID, but there are some people that say PID. So Z is a PID, and then from our previous example, we know that Z bracket X is not a PID. Okay, so that's a good place to stop, and what we'll see in coming up, right? We're going to study principal ideal domains and the properties of principal ideal domains quite a bit. So we'll see why we care about such things in the near future. Okay, so we'll see you next time.